Hello students, welcome to another tutorial on projectile motion. In this tutorial, we're going to look at this interesting question. I got this question from one of my students and I thought you guys might want to take a look at it. It's something very interesting, a little bit tricky, but it is manageable. Let's see what they're asking. Well, it starts with a statement. The statement says, for any angle less than 45 degrees, there is another angle greater than 45 degrees, which will have the same range. And to find that second angle, from 90 degrees, subtract that angle which is less than 45 degrees. That's quite plain and easy to understand. Now, what's the justification? Well, to understand this, you have to look at the simulation. But generally, what is happening is that when you fire a projectile, you have one angle through which the projectile will achieve a maximum range. What will happen? This angle, of course, it occurs at 45 degrees. So at 45 degrees, any projectile will have a maximum range. But as you reduce the angle, if you reduce the angle, the projectile will not go very far. Instead, it will land a little bit nearer. The more you reduce the angle, the closer the projectile gets. Now, apart from this, if you try to increase your angle, trying to take the projectile even further, the problem with that is the projectile ends up gaining too much height such that its horizontal distance reduces in the end. So instead of gaining more range, you actually reduce. So increasing the angle again doesn't achieve anything. It actually reduces on your range again. So now we see that the more you increase, the more your range reduces. So we're saying for every angle less than 45 degrees, there will be a similar angle greater than 45 degrees that will give you the same range, but only 45 degrees will give you the maximum range for your projectile. Okay, for anyone who's ever tried to play javelin, I think you should understand this very well. If you try to throw your projectile at a greater angle, it doesn't actually go very far. It just goes way higher, but in terms of range, it doesn't go very far. And if you try to throw it at an angle way too small, the projectile fails to go very far. Why? Because it lands way too quickly before it can even go very far. For you to achieve the best result when you're playing javelin, you have to throw your projectile at an angle 45 degrees. In that case, your projectile is going to go the furthest with the same velocity. Okay, with that statement, let's quickly come back to see how we can actually work out these questions given for an example. Let's look at the case of an arrow. So here we have an arrow that leaves the bow with a velocity of 30 meters per second. Okay, what are they asking us to find? Well, in the first part, they're asking us one thing. What is its maximum range? So if you have an arrow that leaves the bow at 30 meters per second, what is going to be the maximum range of this arrow? Well, it's quite simple, really. All you have to remember is, for you to achieve the maximum range, the angle this arrow has to be fired at has to be 45 degrees. So in this case, for part A, our approach is very basic. So we want to fire this arrow such that the angle is 45 degrees. And of course here, the assumption is that the arrow comes to land at the same level. So we expect the arrow to go up and then eventually come down. So let's assume this is the part where we get the maximum range. So the velocity it is fired at is 30 meters per second. Okay, now how do we work it out? Well, just like we saw in earlier questions, to work this one out, want to find the range. All you have to do was just to remember that the maximum range is achieved when the angle is 45 degrees. After this, everything else is really what we've been doing all along. First, you find the time, and the time I'm going to get it in the vertical axis. So the y component of velocity, the initial in the y-axis, will be equal to, from vectors, you just break this to get the y component, which is 30 sine 45. So using this in the y-axis, I can say the final velocity in the y-axis, initial velocity in the y-axis plus acceleration in the y-axis times time. Here I'm trying to get the time for going up in the y-axis. Let me label it as time 1. I'm just looking at the time to go up to the maximum height. The maximum height, the velocity is 0. The starting velocity is a positive 30 sine 45. The acceleration, this is due to gravity, so this is going to be negative 9.8, and then t1. So I'm working this out very quickly because you guys, I hope you've already seen my other videos on projectiles. If you haven't, please find them, or I'll leave a link in the description. Working this out for t1, so all we have to do is make t1 the subject of the formula, and all we're going to have is t1 is equal to 30 sine 45 over 9.8. And here, if we perform the division, we see that t1 comes out as 2.16 seconds. So this is just the time for the projectile to go up. In other words, it's just the time for this part, for the projectile to move from here up to the maximum point, up to just there. Now, to get the total time, all we have to do, since it's landing on the same level, we just have to double this. It's the time for going up t1 will be the same as the time it takes to come down to the bottom, t2. But here's the same, we'll just label them as t1, t1. So the total time t will be the sum of t1, time for going up, plus time for coming down, or just double them. Since t1 is the same as t2, okay, so I've labeled that as t2, so let me keep this as t2. So since t1 is equal to t2, this is just double t1, and this becomes 2 times 2.16, and this quickly gives us 4.33 seconds. This becomes the total time of flight. Why were we looking for the total time of flight? Well, because to get the range, now we're going in the x-axis. And what is happening in the x-axis? Well, in the x-axis, there is no acceleration. And since there is no acceleration, we are going to use the definition of speed. So in the x-axis, we're dealing with the definition of speed, and speed is equals to distance over time. Well, the distance is the horizontal range, that maximum distance we're looking for. So I can say distance is our range max. In the time, we just found what that time is from the y-axis. The time it takes to go up and come down is actually the time it took the projectile to move all the way. So this can be 4.33. The speed in the x-axis is the x component. That x component of the velocity will be maintained. So if you take the x component of the velocity, you should have 30 cos 45. So this becomes the x component of the velocity. So therefore, the maximum range, so the range max, will be equal to the total time, 4.33, multiplying the x component of the velocity, 30 cos 45. So if you evaluate this, you get the maximum range as 91.84, or you can write this as 92 meters if you're dealing with two significant figures. Okay, so this becomes the maximum range for this projectile. The maximum range for this projectile. The second part of the question is asking us for something else, something a little bit more complex. You guys are going to find this interesting. It's a little bit tricky, but I hope you're going to appreciate it. What are they saying? At what two angles could the archer point if it is to reach 70 meters? So now we want this arrow to reach 70 meters. All we want to do is to find the angle at which this archer must point. But take note, the velocity is still that 30 meters per second. So what are we looking for? We want to find the two angles. Remember, one has to be less than 45, the other one is greater. So what two angles? So let's say this is the first one. Let's label it as theta. The velocity is 230 meters per second. So when this is the case, the projectile goes up and then it lands at some point. But this time around, the projectile lands at a point 70 meters from the launch point. So the range is now 70 meters. Now, the first thing is we're going to find that angle less than 45. Then I'm going to use the angle less than 45 to find the other pieces. We were told that the second angle will just be 90 minus whatever this theta is. This is how we're going to find the second angle. Now, first, the problem is getting this initial or this first angle theta. How do we do that? Well, stepwise. You see, for this question, you have to be very, very careful. It's a little bit tricky, but still, let's see how we can work it out. I'm going to use the ideas of displacement here. And of course, in the x-axis, I'll still use the definition of speed. So I'll break down this velocity into the x component and y component. For the x component, so the x component of the velocity, I can say u in x. This is just going to be 30. I don't know the angle, so I'll just say cos whatever this angle is. And in the y-axis, u in y, what I have is 30 sine whatever this angle is. So in the x-axis, what is happening? Well, in the x-axis, all we know is we're dealing with the definition of speed since there is no acceleration. So what we have is the distance divided by the time. Now, in this case, we don't know what the time is. So we're just going to label the total time as t. The distance, we're given what the distance is. This arrow is to cover a range or a horizontal distance of 70 meters. But time, let's say the total time is just t. The speed, on the other hand, the speed of this projectile is the horizontal component, which is 30 cos theta. From here, we can make t the subject of the formula, and this expression becomes t is equal to 70 over 30 cos theta. Let's hold on to this as our equation 1. Now, how about in the y-axis? What is happening in the y-axis? Well, in the y-axis, we're going to take a shortcut. We're just going to, instead of looking at it going up and then coming down, we're just going to look at one simple fact. In the y-axis, this projectile just goes up and then it comes down to this particular point. So if we look at it, its initial velocity in the y-axis is that velocity it was launched with, but its y component, sine theta. The acceleration in the y-axis is negative 9.8 meters per second squared. The final velocity here, we're not really interested in it, but the displacement, this is the key thing. If we look at its motion, it starts from point A, it lands still at point A. So the displacement, the total displacement of this projectile in the y-axis, the displacement is just going to be 0. I hope you've got that. It goes up, then it falls to the same point in the y-axis. So in other words, the vertical displacement is 0. So this is very important in our description. But what we want to come up with is an expression for that connects the time to that angle. So time is what we're interested in. Notice that using this approach, it kind of gives you the total time for going up and coming down without having to think about T1 for going up, then T2 for coming down. This approach just gives us directly the total time of going up and coming down. Okay, now we see that here we've got no use of the final velocity, so we're just going to use the initial velocity. That brings us to this equation. S is equals to ut plus half at squared. We're just in the y-axis here. S is the displacement, but because we're landing at the same point in the y-axis, the displacement is 0. Initial velocity is 30 in the y-axis sine theta, but then this is multiplied by the total time t. So this is plus half. The acceleration is still at 9.8. It's negative because it's going down, and then total time squared. Okay, so from here, we then have to just simplify this equation a little bit further. So what we see here is that when we try to simplify this equation, let's see what happens. This becomes 0 is equal to, we can have 30 sine theta t, and then the negative comes outside. This becomes 4.9 t squared. Okay, this equation, you can continue simplifying it a little bit more. If we rewrite this, what we're going to have now is, I'm just going to make the 4.9 t squared positive. So this is going to be 4.9 t squared positive. When I just move on the other side, or when I multiply it by negative 1, this becomes positive, but for this to be positive, then the other term has to be negative 30 sine theta, then t, this is equal to 0. From here, I can factor out t. This is a quadratic equation. I can factor out t. So now what I have is t, open bracket, 4.9 t minus 30 sine theta is equal to 0. What this means is, from a mathematical point of view, either t is equal to 0 or 4.9t minus 30 sine theta is equal to 0. At this point, quickly notice one thing. T is equal to 0 doesn't help us. It's kind of meaningless for our question, so we can't really work with this one. So let's drop this one. So let's work with the remaining equation. So what we have is 4.9t minus 30 sine theta is equal to 0. We can kind of make t the subject. The formula doesn't matter which one we want to work with. I can even make the 30 sine theta. So this becomes 30 sine theta is equal to 4.9t. At this point, let's hold on to this as our equation 2. Now, if you look at equation 1 and equation 2, from equation 1, we had t, the expression for t, and t was equal to, so we had t is equal to 70 over 30 cos theta. This was the expression we had for equation 1. So now what we're going to do is we're going to substitute equation 1 into equation 2 where we have t. So this becomes 30 sine theta from equation 2, and then now we have 4.9 times where we have t, we're going to put 70, 30 cos theta. At this point, we just want to work this out a little bit. We can simplify this a bit. This becomes 30 sine theta is equals to 4.9 times 70 over 30 cos theta. Here we can cross multiply, and if we cross multiply here, this is over 1. Now we're going to have 30 by 30 by sine theta. Then this is cos theta is equals to 4.9 times 70. This is now what we have. Now the next part is we can multiply this part. This becomes 900 sine theta cos theta is equal to, and when we multiply this part, we get 343. Okay, at this point we can divide both sides by the coefficient, this side, and what we're going to have is sine theta cos theta is equal to the 343 divided by 900. We can keep it like that anyway. You can have 343 divided by 900. Now we reach at this point. We can even keep this as our equation 3. Now, equation 3 is a little bit tricky. What we have is sine theta cos theta. Sine theta times cos theta equals to 343 over 900. This might be a little bit tricky, but luckily we have a trig identity that can help us to simplify this. You see, what we want to find is theta, not sine theta times cos theta. We want to find theta, but it's kind of a little bit tricky for us to isolate the angle when we're dealing with the two angles like that. But we can use a trigonometric identity. So if we remember trigonometric identities, you guys should remember that sine theta cos theta, provided these angles are the same, then from trig identities, this is going to be equal to 1 over 2 sine 2 theta. So this is the trig identity that we are going to use. So note that this is just coming from double angle identities. Okay. So from here, we can then substitute this where we had sine theta cos theta. So in equation 3, or from equation 3, we had this cos theta equal to 343 over 900. So where we have sine theta cos theta, we're now going to plug in that value. This becomes 1 over 2 sine 2 theta is equal to 343 over 900. Here we can work it out for sine 2 theta. Then this becomes sine 2 theta is equal to 2 times 343 over 900. And then from here we can evaluate the sine inverse. So sine inverse means that we're just going to remember the argument here. 2 theta is equal to sine inverse of 2 times 343 over 900. Once we've achieved this, the next thing is now just to evaluate what the sine inverse is going to give us. So sine inverse of that argument is going to give us 49.66 degrees. But then we want theta, not 2 theta. So divide both sides by 2, and our angle comes out as 24.8 degrees. So this becomes the first angle. Now, our question says that if this is the first angle, the one less than 45 degrees, to get the second one, let me label it as phi. All we have to do is from 90 degrees, subtract the first angle, meaning that we have 90 degrees minus 24.8 degrees. The second angle then comes out as 65.2 degrees. So in other words, for our question, we've now seen that the two angles which give you the same range, it's 24.8 degrees and 65.2 degrees. Now this method was a little bit long, and you might think that it was a little bit tricky. So you might be doubting to say, well, are these two angles actually correct? And if they are, will they actually give us the same range? So you might want to actually test them. So let's quickly just test the first one, and then you guys can test the second one and see if it will give us the same range as the first one. Now, how do we actually test it? Well, to test it, let's see, since we were given the range to be 70 meters, I want to see if we projected this arrow at an angle 24.8 degrees with a velocity of 30 meters per second, will it actually have a range of 70 meters? Let's see if that's the case. So of course, the first thing is, want to find the time it reaches the maximum height. Okay, want to find the time it takes to reach the maximum height. At the maximum height, the velocity, final velocity is 0. The initial velocity, it is in the y-axis, so it is going to be 30 sine 24.8 minus 9.8 t1. It's the time for the maximum height. So what we're going to have is t1 is equals to 30 sine 24.8 over 9.8. Here I'm a little bit quicker because the methods we use, these are the same methods we used in the earlier question. So you guys should be able to work them out if you saw that earlier. Just the first part of the same question. These are the methods we used. So T1, time up to the maximum height, if you use this, is going to come out as 1.284 seconds. This is time just the maximum height. But since the projectile lands at the same level, so it takes 1.284 to go up, it takes the same time to come back down. So the total time T will be just double that T1. Again, I only do this, the double part, if the projectile lands at the same level. So in other words, the total time to go up and come back down becomes 2.57 seconds. Now that we've got the total time, we can try to use this now in the horizontal axis to find the range. So the range in the horizontal axis, we're using the definition of speed since there is no acceleration. This is just going to be distance over time. We know the total time, that's the 2.5 seconds. So here all we're doing is cross multiplying. So the distance, which is the range, of course, is just going to be the speed. The speed is the x component of that 30 meters per second. So it's going to be 30. But now it's cost to get the x component, 24.8, multiplying the time, 2.5 seconds. If you do this, you will see that the final answer you're going to get is going to be 69.9 meters, which can be written approximately as just 70 meters. So you've seen that we've actually obtained the same range which we were looking for. Now, what I want you guys to do is try to test that 65.2 degrees. Try to see if it will also give you the same range. So you start first by using, instead of 24 here, 24.8, you will use 65.2. So you use 65.2 here, and then you also use 60, which means 65.2 here. It's going to give you a different value of time here. But don't worry, just continue doing the math. You're going to have a different value of time, but you use 65.2 here again, but you see you still end up getting the same range. So try to do that as well. Let's see what you're able to find. All right, let me know what you think. At the time I looked at this question, I thought it was a little bit tricky. Do you agree? Was this question a little bit too tricky? Let me know what you think in the comment section. Otherwise, we'll see you guys in the next tutorial. This was your tutor.